The other thing we looked at was this map of the outgoing long wave radiation, and looked at the high values where subsidence happens and clear skies, so more energy is going out to space. And we looked at these bands of low OLR in the low latitudes, which is obviously related to the cold cloud top temperatures. Remember, outgoing long wave radiation sigma T to the fourth, if it is low, it just means temperature is low. Obviously that is coming from the cloud top, and that means there is deep convection, right? So this was a good indication of where the convection was happening in the atmosphere. We can look at properties in the ocean in a similar way. Let's start with temperature and salinity. I'll show more figures when my Wi-Fi comes back. So here is the annual mean sea surface temperature distribution. As you can see, there are warmer temperatures in these darker green colors in the low latitudes, and as you go towards the poles, then the colors fall off towards white. Of course, these are snow and ice, which we're not talking about. We're just talking about water temperatures, which get colder at higher latitudes. But you can see that there are zonal asymmetries. Remember, we talked about zonal asymmetries when we talked about the eddies in the mid-latitude atmosphere. Similarly, we have colder temperatures here, and this is not obvious, but there should be some here as well. So, and there are warmer temperatures here. Okay, so obviously the ocean, even in the deep tropics, has a very strong zonal asymmetry, and that asymmetry has a seasonality. So in the winter months it is bit warmer than in the summer months. Why does it get cold here? We will see that that is related to the trade winds that we have already looked at, and the Coriolis effect that we have already looked at. Remember, Coriolis pushes things to the right of the direction of motion in the northern hemisphere and to the left of the direction of motion in the southern hemisphere. So if northeast trade winds are pushing westward this way, southeast trade winds are pushing westward this way, then water is being pushed to the right in the northern hemisphere and left in the southern hemisphere, which means water is diverging away from the equator. What does that mean? For mass continuity, obviously you have to bring up water from below, and water below is colder. So we have what is called upwelling, and as the ITCZ had a seasonality, the trade winds also have a seasonality. So the colder temperatures are going to occur when the upwelling is maximum. Okay, so we'll look at those details later on. How does salinity distribution look? I will show later on that this is closely related to the evaporation and precipitation in the atmosphere. Remember, this is where the subtropical gyres are, and you don't see it so clearly in the temperature, but you see it much more clearly in the salt, salinity at the surface. These are the regions where Hadley cell is subsiding. There are clear skies, there is high evaporation. Remember, the Hadley cell is being supplied moisture from the subtropics into the tropics, and that moisture is coming from evaporation. Evaporation leaves salt behind, so you have maximum salt in those regions. And you'll see a strong contrast here that the Atlantic is much saltier than the Pacific at similar latitudes in the subtropical gyre. So Atlantic turns out to be very different in many ways. We'll see here that the salinities are order 35 and 35.5, whereas here they're order 33. This makes a difference because, remember again, density is dependent on salinity and temperature. So various processes are related to this. Indian Ocean is different, as we will see, because of the monsoonal circulation, which changes with seasons, and the Southern Ocean obviously is different because it's a channel as opposed to these basins where there are boundaries. we'll look at all these sorts of things, but looking at the vertical section, because the ocean has boundaries, it doesn't really make that much sense to make zonal mean meridional sections that we kept looking at in the atmosphere. Nonetheless, it's been done here, and you can see that there is a typical structure with deeper isotherms here. This is actually potential temperature, so you can see the potential temperatures dip in these regions. What is there? That is the subtropical gyres. We will see that the currents converge and waters are pushed down in these regions. So where there is upwelling, there is lifting of the temperature isoplets or isotherms or isopotential temperatures or isentropes. Whereas water converges, you get warmer water coming deeper. But as you go to higher latitudes here at 60 north, for example, there is a collapse of the water column, and temperatures, uniform temperatures, are going down quite far. And we'll see similar behavior here, and we will see that all these are related to wind-driven circulation and density-driven circulation in the ocean. You also see that this is an expanded scale of the top 1 kilometer, whereas this is going from the surface to the bottom down to about 6 kilometers. So you can see that the upper ocean high temperature gradient regions are just within the top 1 kilometer. That's where a lot of the fast seasonal changes happen. When you go deeper, there are hardly any fast changes. The whole thing is really moving slowly, changing slowly, and so on. So to look at salinity as well, you see high salinity regions that we saw in the map being brought down with the circulation. So you can think of this as the oceanic Hadley circulation, where the upwelling in the atmosphere we had convection and rising motion. In the ocean you have upwelling and rising motion. The rising motion is supplied by these circulations coming in from the subtropics. So this is like the ocean's Hadley cell. Upwelling water is going away from the equator in sinking here and coming back. So you have, similar to the Hadley cell in the atmosphere, you have Hadley cell in the ocean. These are called subtropical cells, as we will see later on. Again, you see there are salinity structures that are penetrating deeper as opposed to the subtropical gyres where high salinity is coming down. Here you have fresh water coming down quite far deep. There are relations to Mediterranean water coming in and its impact and so on, but you can also see certain density structures that will be created by a combination of these temperatures we saw before and these salinities. So it's kind of a very hand-wavy argument, but keep these things in mind, the general meridional structure of temperature and salinity in the ocean, and we'll connect them to circulations in this chapter and the next chapter. This is the potential density, which looks a lot like temperature, because temperature has a heavy control on ocean density in most places. So you can look at a typical density surface. Density of 26.5 basically means sigma of 26.5, as you can see here. So in the ocean it's very common to carry sigma rather than total density. Why did we take sigma 26.5? Because it's kind of in the middle of the thermocline, which we didn't explicitly define, but the regions of sharp gradients of temperature. You can barely see here, but the temperatures are well mixed near the surface, as we will see later on, and there is a sharp gradient before you go to the fairly uniform deeper ocean. Okay, so the 26.5 is in the middle of this sharp density and temperature gradient region, or the thermocline, and you can see in the subtropical gyres it's deeper. 26.5 goes deeper. In the upwelling regions it's lifted up. There are other details here under the ITCZ and so on, and the oceans are different from each other. Climate variability actually is closely tied to the zonal extent of these basins, because the signals propagating back and forth depend on how big the ocean is between its boundaries. Okay, so in the atmosphere we briefly mentioned waves and wiggly things in mid-latitudes which can go around, whereas in the ocean nothing goes around except in the Southern Ocean, right? So all these things actually matter. So that gives you a brief sense of how ocean is remarkably different from the atmosphere, but nonetheless it has similar large-scale balances in terms of geostrophy and thermal wind and so on that we will see, which are riding on top of this wind-driven circulation and density-driven circulation.